All right, let's start by recalling the definition of similarity. We say matrices A and B are similar if there exists a matrix P that's invertible such that A equals P, B, P inverse. All right, so this diagonalization stuff, which we use a lot of in this course and in linear algebra in general, is tied to this. So definition. A is a diagonalizable matrix if A is similar to a diagonal matrix that we normally call D. So in other words, A equals P, D, P inverse for some diagonal matrix D. So let's explore this, and then in the next section in this section and the next one together, we'll see why this is so important. So here's an example, a motivating example, mote X. Okay. Let A be the lovely 2 by 2 matrix, 7, 2, minus 4, 1. Let P be the magical matrix, 1, 1, minus 1, minus 2, which is invertible. Its determinant is negative 1. And P inverse turns out to be 2, 1, minus 1, minus 1. Okay, so let's compute. So I'm going to unravel this. So let's compute P inverse AP, which is 2, 1, minus 1, minus 1. A times P, 1, 1, minus 1, minus 2. And we do the multiplication from right to left, so we get, make sure I get my notes here. And you wind up with the matrix 5, 0, 0, 3. So, I chose A to be this diagonalizable matrix. And so now, looking at the multiplication here, A is going to be P times our D, P inverse. So A is diagonalizable. All right. So let's explore this matrix A for a minute here. So let's first of all let's compute the eigenvalues of A, which is just taking the determinant of A minus lambda I and setting it equal to 0. So this determinant is 7 minus lambda, 2 minus 4, 1 minus lambda. That equals 0. If and only if lambda minus 7 times lambda minus 1 plus 8 equals 0, which is true if and only if lambda squared minus 8 lambda plus 15 equals 0, which is true if and only if lambda minus 3 lambda minus 5 equals 0, which is true if and only if lambda equals 3 and 5, which turn out to be the eigenvalues of A. Oh, wow. Let's see here. these two numbers happen to be in this matrix, in the diagonal of the diagonalizable A. Okay, that's convenient, because now we have a way of turning A into a product of a diagonal matrix and relating it to its eigenvalues. So let's keep going. Let's find the eigenvectors of A. I think you know where this is going, but we'll go through the grubby details. Let's let lambda equal 5. And now we're going to solve A minus 5I x sub 1 equals 0. And when you do that, you get 2 minus 4 minus 4, which row reduces to 1, 1, 0, 0, and says that x1 is 1 minus 1, or any multiple of it. Okay, let's go to some blue here. So look at that. Look at that vector. And then let's look at, where's P? Oh, the first column of P is 1 minus 1. And our eigenvector is 1 minus 1. Okay, so now let's let lambda equal 3. And we compute A minus 3I x2 and set that equal to 0. That's a vector. And with a little bit of work, you get that it's the second column of P, 1 minus 2. Now, I don't know what's cooler than that, but so this diagonal, so here's theorem 5. So let A be, so a square matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. And this is true if and only if the columns of P are the n linearly independent eigenvectors of A. And this is true if and only if there are enough eigenvectors to form a basis for Rn. All right, and it's also important to note the eigenvalues in D must correspond to the eigenvectors in P. So going back to P and D from before, so for example, let me do this right here. Going back up here, P was 1 minus 1, 1 minus 2. So here's P, and D was 5003. And what the point I'm trying to make here is that column 1 in P needs to correspond to the column that has the eigenvector that matches the eigenvalue. And so column 2 here corresponds to the eigenvalue lambda equals 3. Okay, so here's a little more interesting example. Let A be the matrix 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. With a little bit of work, we get the eigenvalues of A turn out to be 1 minus 2 minus 2. So note that lambda equaling minus 2 has algebraic multiplicity equal to 2. Okay, and now for A to be diagonalizable, we have to have n equals 3 linearly independent eigenvectors. So if lambda equaling minus 2 is degenerate, in other words, its geometric multiplicity is strictly less than its algebraic multiplicity, this doesn't work. So we're going to explore that too in the homework problem. So for lambda equaling 1, the eigenvector, according to this guy, is 1 minus 1, 1. And 2, for lambda equaling minus 2, the eigenvalues corresponding to this guy are minus 1, 1, 0, minus 1, 0, 1. So note that the dimension of the eigenspace corresponding to lambda equaling minus 2 is 2. And in the dimension of the eigenspace corresponding to lambda equals 1. And 2 plus 1 equals 3, which is the dimension of R3. So we have enough, basically, to create P. Okay, so P, and I'll create D at the same time. So D has diagonal eigenvalues 1, 0, 0, 0, minus 2, 0, 0, 0, minus 2. And the order in which you choose this guy doesn't matter, but how you choose P does matter. So the eigenvector corresponding to this guy is 1 minus 1, 1, and that has to go in the first column. And then the other two go here and here. And if you don't believe this works, remember we're supposed to show that A equals, is it P first? I think it's P first. Yeah. P, D, P inverse. Now, computing inverses is not nice. So what you want to do is multiply on the right by P inverse. And so if you compute AP and you compute PD, you get the same check without having to find what P inverse is, which for a 3x3 is an absolute nightmare by hand. And even if you do it with a computer, once you start getting into 3s, 4s, and 5s, it starts doing round off error, and you'll get like 3.00001 for the eigenvalue. But it's much cleaner if you use that. Okay, so what we saw in this example is that the eigenvalues don't need to be distinct for this diagonalization to work. And that's really the interesting case here, because, well, here's a theorem. Theorem 6. This is sort of boring but true. if A has n distinct eigenvalues, then n is diagonalizable. Right, so for each eigenvalue, you get exactly one eigenvector. So there's going to be n, so it's going to make a basis for Rn. Theorem 7 is the fun one. So let AB square, let AB square, and the eigenvalues of A are going to be the set lambda 1 down to lambda p. All right, so for each lambda sub k, k equaling 1 down to p, so k is our index here. The dimension of the eigenspace of lambda sub k is less than or equal to the algebraic multiplicity of lambda sub k. 2. A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n, because now you have n linearly independent eigenvectors, and you can create this P, which would be invertible because the columns are linearly independent and there's n of them, so it's a square matrix. And then C I don't like C in the book, so our theorem 7 will just be A and B. Pulling rank on David Lay there. All right, that's all I got. I really want to flesh this out in person because these questions are some of my favorite to hit you guys with. And so I'm not sure what homework problems I'm going to assign, just like last time, so we'll wait. Although homework isn't due until Wednesday, so I might hit you with some of these. So let me think here for a second. This is homework 6 that's due Wednesday. Yeah, and I'm definitely going to add some. I'll figure it out and get back to you. Enjoy.